4D on key stage 3, year 7. I shouldn't do that. I should decline that request, but I'll see when I look at it. Um, why is this not a complete circuit? Does anybody know? This is one that I'm not sure anybody quite recognizes. Can we see what's wrong with this circuit? It's very hard to see this unless you've seen this question before. Like when the first time I saw this, I would not have recognized this. See if anybody knows. Can you see the problem with that circuit? The bulb is the problem with that circuit. So effectively, what's supposed to happen is the electricity will flow through here, flow through here, flow through here, and then come back here. That's essentially what happens. But because this is a broken bulb, um, yeah, that's why it doesn't work. I won't write that down. In diagram 4, why is there a reading on this ammeter? It's because we have a complete circuit, or the circuit is connected correctly, is what I would say. Okay, that's right. What was that? 2, 3. Someone has said 4D. Let's see what 4D says. Which metal is usually worst used for wires? I'll just tell you that. Copper is most commonly used for wires in electric circuits. Okay, try and remember that because it is so fundamental across 3 different sciences when it comes to this. Okay. Goodness. Right. Okay. B3, question 4. I assume that means booklet 3. Hello. Again, I'm going to come to booklet 3 after this one. I'm going to do this in order. So 2, 3, and then somebody said 5. 2, 3, 5, and then 9 and 10. Right, that's the last one on me. 5. Connect these symbols to make Joe's circuit. Okay. Right. I mean, I'd probably just redraw it again and go battery, bulb, and then switch. Something like that. Just put it together into one circuit. That's how we draw a circuit. Not very nicely done that. Make it a bit bigger. Yeah, something like that would be probably what I would do. I mean, I guess you could just do this if you wanted to. That would also work. I've just redrawn it again. I don't have the question booklet. I did it like, but you should have a question booklet 'cause I would have given you one. But anyway, um, Joe closes the switch and the bulb lights up. Bulb lights up. Then she connects the battery the other way around. What happens to the bulb when Joe closes the switch again? So we close the switch and the bulb lights up, obviously, because we completed the circuit. Then she connects the battery the other way round. What happens to the bulb when Joe closes the switch again? Well, you see, I think it's exactly the same because you putting the battery the other way round doesn't affect it in this circuit because all it does is, if I swap that over, it just means the electricity flows the other way around and everything still works. It is still a complete circuit. Okay. Right. A corridor has a switch at each end and one light bulb in the middle. The circuit diagram below shows how they are connected. Right, okay, weird. Oh, jeez, so complicated. In the diagram above, the switches are shown in position B and D, and the bulb is on. Complete the table to show whether the bulb is on or off. So we're going to switch 1 at A and switch 2 at D. So it's almost like, so like now, as it is now. Okay, so let's do this in red. So switch 1 is at A, switch 2 is at D. So is this going to work? We have a power supply. It's going to go like this, but then it's got nowhere to go. Remember, this isn't here because I put it on A. So that means this is not going to be a complete circuit and the bulb will not light up. It will be off. Whereas now it says position 1 is at A, position 2 is at C. So the first one is at A and the second one is at C. Will this work? So go back to the power supply, battery. Will it get a complete circuit? Yes, we can. We can get back to where we started. So therefore, the bulb will be on. That's how we do this. The circuit is changed in a weird way so that there is a bulb at each end of the corridor. In the diagrams above, the switches in B and C, which bulbs, if any, are on? So let's have a look. We have a power supply that goes there. Now, which way does it go? Well, I guess some of it's going to go there. Some of it's going to go there. But we don't get back to the power supply this way. So I think that none of them are on because we just don't have a complete circuit in any way. There's no way we've done that. So that's the way to do these questions. Can you connect one end all the way around? The switches are arranged so that both bulbs are on. Bulb X breaks. So now they change it. So let's say it's on right now. Okay. So let's say we've just done this, right? So everything's on. And remember, because of this, this can go this way as well. The question is, says bulb X breaks, what happens to bulb Y? Well, I don't think anything happens to bulb Y because of the way we've set up this circuit. Because even if bulb X breaks, we'll get a complete circuit this way around. Do you see what I mean? We can still get from one end to the other using a different route because the way we've set it up. It's called a parallel circuit. Um, so we have done that. Right, so bulb Y, nothing happens to it. It stays on. Okay, two, let me go back to the beginning. What was the questions earlier on? Um, two, three, five, I've just done, and 10. And then, did anybody else answer question nine? Nine and 10, probably. I don't think I'm going to do question seven. Yeah, only because you asked quite late. Um, nine, right. Oh, it's easy. Draw a line from each circuit to the correct diagram. We have a battery, and then there's three bulbs. So surely that's just that one. Here we have a battery, and then two bulbs, and then one bulb. So surely that's this one. We have a battery and three bulbs all in line with each other. So surely that's this one. And then we have a battery and two bulbs. So that's surely this one. Yeah, it's relatively straightforward. Um, and then this whole breaking thing is always interesting. Um, In each circuit, bulb one breaks. In each circuit below, bulb one breaks and then goes off. Tick, so if bulb two and three are off. So this is called a series circuit. You should all have done that. In a series circuit, one of the key things is if the one bulb breaks, everything else turns off as well. That's it. So they're both off. Whereas in a parallel circuit, if one breaks, the other two stay on because we still have a complete circuit. Sorry, I don't know what I did there. It's ticks, I think. Give the name of the part that provides energy for each circuit. It's the cell or the battery. Battery is what we need. And why is copper used? It's a good conductor of electricity. Question 10. Last one I'm going to do from this booklet, and I'm moving on. Susan has a small fan to keep herself cool. When she switches it on, the motor turns blade to blow air. Right. Draw a series circuit for the fan using these symbols. Okay. Again, really simple. A series circuit is just a big rectangle. That's all it is. And therefore, all you do is put these diagrams or these symbols on that thing. So here is my battery. All I need is a motor somewhere on the rectangle. I need a switch somewhere on the rectangle, and done. I mean, that's lovely. Which part provides energy for the circuit? Again, the battery is the thing that provides it. Um, Energy is wasted usually as heat. Let me just check what it says. Heat or sound. Yeah, heat and sound. Either of those two is the answer. Um, Susan built a circuit using a battery motor and a switch. She closed the switch. The current decreased. How did this affect the motor? It turned more slowly. So the equivalent, if you basically add things to a series circuit, you decrease the current in the circuit, which means that everything in it will work less better. So a light bulb will be less bright. A motor which spins will spin more slowly. Then what they did was remove the motor, the current in the circuit increased. How did this affect the bulb? Well, if the current increases, the bulb gets brighter. And that is all of that. Right, I'm moving on to. I don't think anybody said anything in booklet two, but if anybody does say anything, please tell me. I don't see anything immediately from booklet two. So, we will go back to 4E 9, because you asked that ages ago. I've got a feeling it's a long one, isn't it? No, it's not. Um, I'll just tell you the answer to this. Again, you may not have done this in the lesson, but it will be in your online notes if you do actually care to look at those because I made a video on doing all of this at some point. Um, right. I'll just tell you what the answer are. This is the graph for a lamp or a bulb. If you look at this S shape and try and remember it for future, then you will be okay. This is the graph for a resistor at constant temperature. Because if a resistor is at constant temperature, it means that the resistance doesn't change. And if it doesn't change, you always get a straight line here. And then the next one's going to be a diode, isn't it? Yeah, that's a diode. A diode is a component that only allows electricity to flow in one direction, which means you don't get this negative section of the graph. You only get this positive section. 4E, done. Right. Anything else? Are we done? Um, Booklet 3, question 4, someone has said. Oh, that was all of question 4. Right, I'm not doing all of it. Um, Oh, actually, I'll just do this. So this is basically, I know it's a bit weird, but that's quite, I mean, that's a hard question. But I shall tell you, I was expecting more people to ask this question, really, because it's quite a tough one. Um, Question 1A, booklet 2. I will come to that after this. Let me see what it is. 1A. How difficult can it be? Okay. It's just not much space for it, but done. It's a circuit with a bulb and another switch. We've already got the cells. That's it. Right, done. Done question. Um, Use the circuit symbols to draw circuit. What? So this is again a difficult question, but we're going to have our battery, however it looks. We're going to have a ammeter in the circuit. We're going to actually have to have something called a variable resistor in the circuit. I think this is quite a complicated question. Okay, I wouldn't really expect you to know it that well. We're going to have a lamp in the circuit, and we're going to need a voltmeter, but the voltmeter goes around the bulb like this. Okay, tough question that. Okay, that's that circuit. But then the next one's even harder. How could the student use her circuit to investigate how the current affects its resistance? Um, okay, let me see what this wants you to do. Okay, I'll just tell you. I'll tell you the easy bit. We want to see how resistance is affected. Now, resistance has a formula. It is voltage divided by current. Okay. What we're going to do is we're going to turn this circuit on and measure the current using what do you use to measure the current? The ammeter. We're then going to measure the voltage. How do we measure voltage? Using the voltmeter. And we're going to then use this formula to calculate the resistance. There is another point here, but I'm not going to write it down, which is the complicated thing, which I don't expect you to know for now. But um, what we then do, because we're investigating how the current affects the resistance, we want to change the current in some way and see how that affects the resistance. We use this to change the current. This is why it's there. The variable resistor can be used to change the current, and that gives you new values for voltage and current, which means it gives you a new value for resistance. Then you can draw a graph and stuff like that with it. Um, Variable? Why do I write variable? Um, Variable resistor. That's it. Okay. Question 1A of booklet 2. I've done it. Done question 1A of booklet 2. It was just a little circuit, um, which was like this, and that was it. I've done it. Right. Is there anything else from booklet 3? Don't think so. Oh, the rest of question 4. Is there more? Describe how the resistance changes as the current through it increases. Well, it increases, doesn't it? It's only one mark. So you can see that if the graph is sloping sort of that way, right, it means that as one thing is increasing, the other thing is increasing. And I think that's it. Use figure one to estimate the resistance when the current is 0.1. So it's a little bit harder, this, but what you've got to do is sort of imagine if you had to continue this graph, where would it go? A bit like that. So at 0.1 is going to go through about there, isn't it? So you just read that way and get that. And that's it, isn't it? Because I did part E already for question four. And I think that's everything. Nobody asked any other questions. Outstanding. Um, okay, as I said, today we're going to be a little bit shorter just because of various reasons. I'm going to return in 20 minutes in case anybody has questions on the uh, I have done question 1D of, no, I haven't. Have I done it booklet 2? I am tempted not to do this because once again, I need you to be here on time. Um, how will the brightness of the bulb change when the cells shown are placed in Bend's circuit? Well, here they'll go off because the battery's the wrong way around. I think there's a problem in this next question. Um, I'm not doing question 7 of booklet 3 because you need to ask the question earlier, I'm afraid. I'm not sure what the problem is in that one. 1D. Um, I think there might be a line missing here, so I'm just going to check. Yeah, there's a line missing in my printing. There should be a line there. And then basically what we've done is increase the number of cells. And if you increase the number of cells, your bulbs get brighter. But here we've put, see how we put it the wrong way around here? It should be big line, small line, big line, small line. We've got one the wrong way around, and therefore it won't work at all, so they'll just be off. Um, Let me check what question 7 of booklet 3 is, and then I'll decide not to do it. I've actually answered that question if you were paying attention to the last question I did. Um, I'll just tell you that. The resistance of the lamp increases because it gets hotter, essentially. That's why resistance can increase with most things when it gets hotter. Right. Okay, as there are no further questions, I'm going to stop that bit there. I will return at 8 p.m. and do whatever any of the year 10 and year 11s want. If they want more, then they are welcome to. I'm afraid I'm not going to do question 4A. Once again, remember, these sessions start at 7:15. What you need to do is get here and put the questions in early on. Generally. I know I'm usually more flexible than this, but I am not in this case. Um, so yes, arrive on time, ask the questions, or even send them beforehand. You're welcome. There's a WhatsApp number. You can send the questions in beforehand, the ones that you're having issues with. At least then I know that you've attempted this before the session begins. Right, I'll be back at 8 p.m. to do some of the year 10 and year 11 questions. Right, hello. Today, for those of you who have just arrived, will be slightly shorter for a couple of reasons. I'm just going to answer any questions that you have on the respective homeworks and not do a great deal else. Most people will have done electricity on the weekend and beyond, whereas on Friday you will have still been doing chemistry, which means that I have opened up somewhere here the chemistry topics, neutralization and analytical chemistry that I did last week. So I'll see what is mentioned here. If you have any questions on it, you are welcome to ask. Hmm. Right. I'll start with the question in order. So this might not apply to everybody, but that's because of the order of topics. So you've asked 2A, question 1, part 2, and 3B. So 1, part 2. This is on chemistry, by the way. So for those of you. Um, 1, part 2. I don't know what that means, but I'm going to go with, is that at the beginning or the end? What's going on? I think that might be question 1, part 2. I'll come back to that in a second. Near the end, yeah, 1, part 2. All of question 13 at the back and 3 on Jesus Physics. So yes, I'll do that. If you have any questions, get them in early-ish, as I said, because I am not going to do after a certain point. This question 1, part 2. I have written down the answer over here, in the sense because I did it last week. Um, whoa, that's not it. That's gone wrong. Yep. So this is probably the most trickiest question on here, so don't stress too much about this. But the idea of this question was that asking you why the reaction stopped, basically. And the reason for the reaction stopping, in this case, even though there was the reactants left, we had this green stuff, which was the acid, and the metal, it was still there. The answer was because this stuff here that was produced formed a barrier in front of on the metal, which meant that the acid could no longer reach the metal, and therefore the reaction stops. That's a quite complicated question, I admit. Um, um, I'll explain once again, is that the certain people in year 10, depending on what day they come, will have still been doing chemistry if your lesson's on a Friday. If it's on Saturday onwards, it will be physics. So I will, in these sessions this month, it will be a little bit of a balance between the two subjects, which I appreciate because there's an overlap. I have to try and help everybody. So yes, it is physics, but some people did chemistry and they will be doing physics on Friday. It's the way our schedule works. Um, so that's that one. Right, question. I'll just get through this quickly and then I'll move on. 2A. Question 2A. Is that the beginning 2A? I appreciate this is really confusing when we've got different numbers to questions at the beginning. 2A was here. So it was explain how acids affects the shells of sea creatures. You need to say the word reacts. The acid reacts with the shells and is them to wear away a little bit or erode. That's what the answer is actually for that. And read B, which I think is the calculation, is it? No, it's not. It's this one. Blue copper sulfate crystals go white when warmed. How could you use the white copper sulfate as a test for water? Well, what we're saying is that when you remove the water from this, it turns white. So how could you use this white stuff to test for water? Well, you could add water to it, and if it turns blue, then it's water. Do you see what I mean? If it turns blue, then we know it's water that makes it turn blue. That's basically all it is. So you could add them to water, and if they turn blue, then that is water. If that makes sense. What was that? Um, Want to see electricity? I want to come to electricity now, I think. And someone's asked, so all right, I think everybody who's asked questions so far, that's pretty what we're going to stick to. As I said, it's going to be shorter today's session for a couple of reasons. I'm just going to get through the questions that have been asked so far. And just for today, it will be shorter. Then we'll go back to lengthy ones next week. All right, I'll try and do this chronologically. All of questions 13 at the back and 3 on the GCSE physics electricity. Okay. Oh, God, this is going to be slightly confusing. You need to say what year you're in when you ask the question as well, because even though it's electricity for everybody, I think the two booklets are slightly different. So I want to go with the year 10 one first. It's going to be really confusing, this. Yeah, I know, year 11. Question 2, year 11. Yeah, okay. Right. Okay, fine. We'll start with year 10. So question 13 at the back and question three. Right, question three. Let's have a look at this. Um, the plug is not wired correctly. What should be done to correct the wires correctly? I think it's the position of something. Um, yeah, it is the position of something. Okay, no problem, no problem. I'm getting there. Um, so it's quite difficult this, but the way the neutral wire is blue. It should be blue, which means the blue wire should be connected there. The earth pin is the green and yellow wire, or the earth wire, which means the green and yellow wire should be there. So you need to swap the um, blue wire and the green and yellow wire. That's what we need to say first to correct that. Then this is just words that, again, we put this in because I was in your GCSE exams, it is very, very possible that you will get a question asking you this, and you just need to know it, that it's a fixed value. The voltage that comes out of your plug sockets is 230. That's what it is. Okay. The frequency, which means the number of times the alternating current changes direction every second, is 50 hertz. That is that. Um, why does heat decrease current? I don't know. I'll check whether that's relevant to a question in a moment. Um, why does heat decrease current? Because well, I think the answer to your question is usually, depending on the component, if it gets hotter, the resistance increases. That's what happens with like a light bulb. As it gets hotter, the resistance goes up, and when resistance goes up, what happens? Current decreases because resistance is something that slows the current down. What is the potential difference between the neutral wire and the earth wire? The answer is zero because it doesn't have a voltage at all. Um, the plug has a fuse. Draw the circuit symbol for a fuse. You should know that, but I think it's something like that, isn't it? Yeah. Um, the washing machine has a metal case. A fault causes the live wire to make an electrical connection with the metal case of the washing machine. The earth wire is not connected. Explain why it not be safe to touch the metal case. Well, because firstly, the earth wire usually takes any problem away so that you don't get an electric shock. So firstly, the earth wire is not connected. So you could get an electric shock. So that's the first point. Um, because if you touch it, current will go through you. There will be current in you, essentially. Um, and that's it. Um, and then the earth wire is now connected. Why is it now safe? Because the whole point of the earth wire is that the charge or the current flows through the earth wire instead of the person, because it basically redirects it away from you. So the charge flows through the earth wire instead. And also, I mean, the easiest answer here. So the metal case does not become live. There's another thing you could say, but I'm not going to say that. Okay, that's that done. Just to be clear, can you say potential difference flows through the person for E? Um, no, because potential difference is a confusing, this isn't it? The words of this is confusing. Um, the potential difference is technically the force that is creating the current, which is or causing the charge to flow. So it is the current that's actually, or the charge or the current that's actually flowing through. I wouldn't say the voltage flows through, or the potential difference is voltage, by the way. I wouldn't say that that flows through the person. It's a bit unfair that I wouldn't say that, but partly because the mark scheme doesn't say it. But oh no, sorry, potential difference. I'm just having a look at the mark scheme now. It says allow because there is a potential difference across the person. Yeah, it works. You'd be fine. I wouldn't do it, but it is fine according to the smart scheme. Right, where are we? Question three is all done. 13 at the back. Let me have a look at that. I'm just doing the year 10 one, so I'm not taking any more questions, by the way, just to be clear, where we're up in terms of booklet questions. Question 13 at the back. Ugh, this looks challenging. Um, okay. A student investigate resistors connecting a series electrical circuit. Right, we've got all of that. Got that. Da, 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 da. Okay. Um, right, this is definitely connected incorrectly because a voltmeter does not go there. If you're measuring the voltage, you need to put it around there somewhere for a start. Um, okay, well now we corrected it. Okay. The voltage across resistor X is 2.1 volts. Okay, so we've got 2.1 volts here. State the value of the voltage across the 22 ohm resistor. Well, it's got to be 0.9 because in a series circuit, the voltage gets shared between the components. It's shared, as not equally, but it is, whatever this number is 3, it is sent both ways. And it's split evenly, not evenly, sorry. It adds up to the total voltage. So it's shared, but not necessarily evenly. The current in resistor X is 0.041. So we've got 0.041 amps. Okay, right. Show that the resistance of resistor X must be about 50 ohms. Resistance is voltage over current. You've got a formula sheet, all of you, year 10, year 11. So you'll be able to get to this equation. Hopefully, the voltage is 2.1. The current is 0.041. 2.1 divided by 0.041 should be about 50, I presume. 51.2. Done. Okay, that's how we would do that. Oh, they gave you the equation anyway, but that's how you would calculate that question. Calculate the power in resistor X when the voltage is 2.1 and the current is 0.041. Again, I might still have it open actually. Let me see if I've still got this open. I do. I have a formula sheet available because I was teaching this a little while ago. Um, when you do this, okay, like I can't stress to you how straightforward this stuff is as long as your maths is reasonably okay. Because you don't need to understand anything that's going on in these questions to get these calculation questions right. Because all I'm going to do, just watch me do this question. I barely will read the question. Bear in mind, this is the first time I've ever seen this question because I haven't seen these questions at the back of the booklet that much. I'm just making sure I want to get this right. Um, yeah, the question asks for power. It tells me voltage. Voltage, by the way, is potential difference on your formula sheet, so potential difference. And it tells you current. So all I need is an equation linking power, voltage, or potential difference, and current. Power, potential difference, current. Power equals potential difference times current. Found it. Okay. And so all I do is take the potential difference, which is voltage 2.1, times it by the current 0.041, and I have the answer to my question. Done. 4B on the year 10 paper. I'm just not able to do much today due to time. I'll see. I'll just look at it now quickly. Um, oh my God, there's a lot of information for nothing. Um, sorry, I just need to think about that question. I think it's hard to do this without looking at everything else. When 4 heat is switched on, the hob draws a current of 26 amps. But if you use these wires, the maximum safe current is only 20. So we learned earlier in the question that if everything's on that cooker, the current will be 26 amps. But the wire, according to the wires, these wires, the maximum safe current is 20 amps. But the maximum that we could get is 26 amps. So we're going to go over the maximum, which means it could overheat and burn and stuff like that. So that's how you explain that question. Right, let me move back to 13. Again, I'm not taking any more questions this time, I'm afraid. That's what I mean. Yeah, anything's already asked is fine. Um, if we get the answer in a decimal, it doesn't say what to round off to. I would normally just do one decimal place unless it says otherwise. One decimal place is what I normally do. It doesn't really matter. The mark scheme gives you a bit of a leeway. If it doesn't tell you explicitly, it will basically leave a lot of margin for error, but I think one decimal place is just a sensible amount. Calculate the overall resistance of the 22 ohm resistor and resistor X. Well, that's 22. Resistor X we said was about 50. I think we worked it out. So we just add them together. About 72. Yeah, that's what that is. Um, right, and then, oh God, there's a formula here, which is a bit of a weird formula, but I think we can just use it in this question. Calculate the energy transferred in 2 minutes. The current is 0.041. The voltage is 3. The time is given to you in minutes. It needs to be in seconds. Times 120. Work that out, and you've got your answer. Okay, that's all straightforward. Let me see what else we've got here. That right, that's done everything, hasn't it? All of question 6, somebody said. Just check how challenging that looks. Right, I really shouldn't have to answer this question, so I'm not going to. 6B. I really shouldn't have to answer this really either. In a parallel circuit, that's what this is. I know it looks like a weird circuit, but it is a parallel circuit. As soon as you see these sort of junctions, it's a parallel circuit because it means the current can go in two different directions. Whereas in a series circuit, it's only got one sort of route to go down. As soon as you basically can follow the line and then choose to go in more than one direction, it's a parallel circuit. Okay. Um, and in a parallel circuit, this is the one you're more familiar with, this kind of parallel circuit. The key rule is that the voltage from the battery is the same on every branch. So this branch gets 6 volts, that gets 6 volts. If this is a 6-volt battery, then this branch gets 6 volts, and that is 6 volts. Calculate the resistance of X. Resistance has a formula, which is voltage over current. At X, we already know the voltage is 6. We know the current is 2. 6 divided by 2 is 3. And what is the current in Y? This is a bit nicer. So the way to do this is to go like this. If we start there, we're at 3 amps at the moment. When we get to here, we have an option. Some of it can go this way, and 2 has gone that way. Some of it can go this way. 1 has gone that way. So it's a 1 amp um, current that's going through Y. Then they want the resistance of Y. Resistance is voltage over current. Once again, it will get 6 volts because everything in a parallel circuit gets the maximum from the battery. That's the voltage, that's the current. Resistance is 6 divided by 1, which is 6. I appreciate I'm doing this quickly, but you know. Um, why can't a voltmeter connect in series? Right, I don't know I genuinely don't know the answer to your first question, other than it doesn't. Right, a voltmeter is connected in parallel, and an ammeter is connected in series. That's all I can tell you. I think it's basic. I think it's because, if you really want a technical answer to that question, is because when you measure voltage, it can be different for different components depending on their resistance. So you can't just put a voltmeter here and go and get the voltage because that doesn't make sense. You can only work out the voltage for a component specifically. So it goes around that component. Whereas the current in a series circuit is the same everywhere. So it doesn't matter where you put the ammeter as long as you put it in line with everything else. In transformers, the resistance current both increase and PD goes up. No, it can't be that, can it? Doesn't make sense. In transformers, does the resistance and current both decrease when PD goes up? So when voltage goes up, current goes down, but the resistance must be going up as well. I'll talk to you about that separately at some point. It's just that there's a reason why that doesn't make sense to me logically, your question. And it's I'll just finish this question first, and then I'll come back to that. When the temperature of resistor X increases, resistance increases, what would happen with potential difference across X? I'm going to tell you the answer to these questions. Um, oof, why is this question 6? Um, yeah. Um, if the temperature goes up, resistance increases. If resistance increases, the current definitely decreases everywhere. The potential difference actually stays the same because it just does. Right, that answers that question. And then I'll move around on to, I think that's all of the year 10 one basically done, isn't it? Yes, it is. Oh, 1C and questions 4B and C. 1C. Okay, I think the answer to the question, without going to the mark scheme, inversely proportional means that as one goes up, the other goes down. Like that's inversely proportional on a graph. It means that as one is increasing, the other one is decreasing. This is not inversely proportional. This is directly proportional because as potential difference is increasing, current is increasing. That's what I would say. Okay. Um, and then for B and C. I did this just now, didn't I? I did that. 4B, I just did. Um, C, what is it with alternating? Well, alternating current changes direction. It alternates direction, whereas direct current only goes in the same direction. That's all for that. Um, and then, right, I'm moving on. Year 11 booklet. I think there's been only a couple of questions from this. So, um, question two. Sure. Ooh, horrible. Why does it start on question two? Okay. Right. I think it's because we shortened it to add stuff at the end. Okay. Does alternating current always switch between positive and negative? Yeah. I think it's a bit more complicated than that because I think you learn about how an alternator works in electromagnetism somewhere else in a different section of the syllabus. Um, um, but yeah, that question doesn't quite make sense because the positive and negative keep switching over, which means that the current switches over. It's not, yeah. Question two. A student investigates how the current flowing through a filament changes the voltage across it. Complete the statement. Okay, I need to read the question. How the current changes with the voltage across it. She's given a filament lamp. Okay. The circuit diagram, again, this is a bit of a required practical, so we are going to do the required practical in a separate session. But what you do here is you need a variable resistor, which looks like this. You need an ammeter. You need oh God, a lamp, because it mentions that. Um, You've also got a switch in the question. Jeez. Um, Switch, right? So I'll put the switch in, and that's it. And then you need the voltmeter, but that'll go around the bulb because you're measuring that off the bulb. Okay, and so what they've done is got these results, which are oh god, that's not drawn very well. Anyway, there. Um, just so you understand, this is again a bit of a technical thing, but if you did this without the variable resistor, you would get one value for current and one value for voltage like that. That's all you'd get, which means on your graph, you would just get one point, right? Which is not a graph. The whole point of the variable resistor is that you can change the resistance in the circuit, which gives you different values for these things so that you can gradually plot the graph. I moved on, unfortunately, from the year 10 booklet, so I won't be doing that. What you need to do, as I said, is arrive at 8 p.m., ask the questions. I'm trying to force people to do this because too many people, I'm not saying everybody, I appreciate some people arrive late for reasons, but I think a lot of people are doing these booklets as we are going along, which is not the purpose of it. So if you've just asked a question in the last 30 seconds, you're 20 minutes late. So I'm not going to answer it. Unless you're lucky and it's already been recorded and answered earlier. Right. Okay, so I don't need to plot the graph, do I? You can do the graph yourself. But it probably looks a bit like this. I'm guessing slightly because I know. Use your graph to find the current when the voltage is 10 volts. So you'd go to 10 up to your graph and read across. Done. Um, Use your answer to calculate the resistance. Resistance has a formula. It's voltage over current. You will not have needed to learn it. You will do 1B. In question 3B, I'll have a look in a moment. Yeah, that is the formula which you will have learned. The voltage they're saying use 10, the current use the one from this answer, and you'll get the answer. What happens to the resistance as the current increases? The resistance also increases. So this is a very specific thing, okay, for a lamp, because a lamp gets hot. As you increase the current through a lamp bulb, it gets brighter, but it also gets hotter. As it gets hotter, its resistance increases. For a lot of components, as they get hotter, their resistance increases. So that's the answer there. And it's because it gets hotter. That's the reason for that's the explanation for it. Okay. Um, right, I don't know what I've just done. What have I just done? Question two. Okay. I don't even know if that was a question. Uh, question two, yeah, it was. Right, and then the only other question from this booklet has been 3B and the question at the end, I presume. Yeah, last one. So that's all I'm going to do for today. Okay, so I'm just going to finish a bit earlier today. 3B. Hmm. Right. Alternating. Um, yeah, I mean, I think that's your question earlier was based on this, wasn't it? It was to do with this kind of thing. Um, the in your sort of IV graphs, okay? Let's say that's the IV graph for a light bulb. This section of the graph is the negative section, right? It's where both things are negative. Now, what both things being negative means in the context of in a circuit is that the circuit is flowing in or the electricity is flowing in the opposite direction. So if that's your battery, let's say it's going this way around, okay, then you would, let's say, get positive values. You'd get these positive values. If you swapped the battery over and it went round the other way, then you would get your negative values. And that's essentially what the tech checking here that you understand is that potential difference can be negative, and that negative is what is the changing direction. All that's happening here is that the voltage is high, then it's slightly lower, then it's slightly higher, then it's slightly lower. That doesn't mean it's changing direction. It just means it's changing. It's going up and then going down. Only if it dropped below here does it show a change of direction. So this question shows that the student was not correct. There's not an alternating current because um, of the fact that the graph shows it's always positive. That's what you're supposed to do. Um, Current increases light intensity. Yes. So voltage and current are kind of intertwined because voltage comes from the battery. Voltage, let me try and explain this. I think we've done the booklet pretty much. Well, let me do the last question, then I'll explain that a little bit. I've never seen the last question before, so it'll be fun. Oh, jeez. Right, okay. Right. Okay. It's an unnecessary question, isn't it? Two students, P and Q, investigate how the resistance of wire varies with its length. That is actually a required practical again, so we might talk about it really when we do that. Um, each student uses different lengths of the same wire and the same equipment. So the data that P obtained. So they basically got these resistances. Okay, right. Resistance per unit length, fine. We'll see what they've done there. Student Q's data. Okay, they've done more lengths, clearly. They've done some random lengths. They've done the same thing. They've done it twice, calculated a mean, and then per unit length, they've got some values here. The manufacturer states that the value for its resistance per unit length is 1.2. Compare the data, which is more accurate and precise. Okay. I would just immediately, just a few points. I'm not going to look at the mark scheme and write loads of things down, but instinctively, I can see that this one uses a wider range of lengths of wire. Do you see what I mean? It uses 10, 20, 30, 40, 50. This one only uses 10, 15, and 19. So it gets a wider range of values. Also, it seems as though some of this data, I mean, some of these values are really far away from each other. 12 and 20 is really far away. 25 and 30, 21 and 29. There's a really big range, if you want to use a mathematical term there, between this data. Whereas here, my values are relatively close together, suggesting that this is way more reliable because it seems like this is a bit of a cowboy experiment and has resulted in lots of different answers. So they're the two main obvious things that I would just notice here. That suggests to me that student Q's data is way more reliable and more accurate and precise, I suppose, for those sort of reasons, right? That's the kind of things that I would say. I mean, I know it's a ridiculously number of marks, but let me see what else we might say. P has taken 3 readings. Q has taken 5 readings. Um, they both use different lengths of wire. Um, Oh, also, I mean, a tiny point here, but we've recorded the length of the wire to the nearest centimeter, point zero. Here we haven't put the point zeros in. That's a rubbish marking point. Um, Oh yeah, here the resistance about the data here as well. Look at that. That's to two decimal places. That's to one decimal place. Again, that shows a less reliability, less sort of useful things there. You could also even say these unequal intervals. It's an interval of five and then four for some reason. Whereas here, at least we're going up in tens every time. So it's just about looking at data and trying to understand what makes data slightly more reliable. Um, yeah, that's it. I think that's enough of that. So, last point, I'm just going to quickly try and get your understanding between four words. I really wanted to do one more thing, but I don't have time. Um, in fact, no, I am going to do it. You know what? Forget it. I'm going to do it. I want to quickly explain charge, current, voltage, resistance. Okay, because I think it's can be sometimes not fantastically understood, these words. Right. First of all, let me just explain what charge is. If I get a piece of wire, like copper, for instance, from chemistry, the reason this material conducts electricity is because, let me just draw that like a wire now. Imagine that as a wire. The reason this material conducts electricity is because it contains delocalized electrons. Remember that phrase? It means free electrons that can move. Electrons are negatively charged. Look at that, negatively charged. Um, And that's what charge is. It is these electrons that are available within the material to move around. That's what charge is. Okay. And it can be calculated by doing a couple of formulas, but ultimately that is kind of what charge actually is. Um, that's what charge, the charge is not the speed of the electrons. Suppose, think of it as just the amount of electrons that are available. So that's what the charge is. It is just how many electrons there are, basically. Essentially, that's what charge kind of is. But that doesn't mean anything technically until we start talking about these things, because current is the speed or the rate of flow of charge. It is the speed at which this charge is flowing around the circuit. That's what it is, right? So the charge is just the sort of amount, right, that you've got that can conduct electricity. But that doesn't mean it is conducting electricity until you have it moving. That's the crucial thing. That's why we need a flow, right? And so current is the speed with which it's flowing around the circuit. If current is zero, then it doesn't, I mean, the charge technically is zero because it's not flowing. It's how much charge is flowing is what, charge is. Um, yeah, that's what charge is. When we say charge, it means how much there is that is flowing around the circuit. Current is how fast it's flowing. Voltage, so these electrons that are in the circuit, right, or in here, I mean, if I just had a piece of metal, it would not do anything, right? It has to be connected to something. The reason it has to be connected to something is because we need a voltage. Voltage is the force that is pushing these electrons around the circuit, right? Without that, they're not flowing. And if they're not flowing, they're not conducting. The whole point of the word conduct literally means that they can carry electricity from one end to the other of a material, right? So they can move. That's why we call them delocalized electrons, the ability to move. But they're not going to move. Doesn't PD do that? Yeah, PD is voltage, sorry. Yeah, PD and voltage are the same thing. They're the same thing. They're measured in the same unit, voltage. Potential difference is voltage. Okay. So it's the force that pushes the electrons around the circuit, and it comes from the battery or from your power supply when you plug things in. That's why things that work as, your devices, so to speak, have to either be plugged into something. So that's where they get their voltage from, or they need a battery because that's where they get their voltage from. Without voltage, none of this makes any sense because the voltage is the thing that is going to move this stuff around the circuit. I could have all the copper in the world. It is pointless. It doesn't do anything for me unless I have something to push the electrons around the circuit, right? And that's why we need the battery. Um, oh God, what kind of force is PD? I'm not going to answer that question. I don't know. Um, but that's where it comes from. It is the force from the battery. Okay, that's what the voltage is. And then resistance is basically the opposite of voltage, because voltage is a force that's, think of it as pushing these things around the circuit. But Resistance is something that's slowing them down, right? It's the opposite. It's like from trying to pull. Sometimes I describe resistance as like a speed bump. Imagine that these electrons are flying around this circuit thanks to the voltage, and then I put some resistance into the circuit. What the resistance will do is it'll slow them down a bit. It's like a speed bump in a circuit. And every component has a resistance. So, for example, this circuit has very little resistance because there's nothing in it. You see what I mean? There is nothing in it. Um, but if I add a bulb to it, I have added some resistance to that circuit, and that's going to slow down or reduce my current a little bit because I'm adding like a speed bump in the circuit. The current is how fast it's flowing around. I am going to slow it down by adding a speed bump or a resistance in the circuit. Right. That's just a little bit of a brief explanation of the differences between those things. I just want to do one thing, which I saw recently in a question, which is why I just want to, for those people who I did teach in the last week, and will already have seen this, but I just want to do one thing because I came across an exam question and I just want to talk about this thing. So this is a series circuit, and this is a 6-volt battery. Now, you know that in a series circuit, the voltage from the battery is shared by these two components. If you put a voltmeter here and a voltmeter here, assuming these two bulbs are identical, they will get 3 volts each. Okay, so there'll be 3 volts effectively going through them. That's what the sort of basic definition of a series circuit is. But my question now is, what if these two were not the same? Okay, let's say there was something else here, like some sort of resistor here. This 6 volts will still be shared between these two, but it might not be shared equally. In fact, we saw that quite literally in a question a little while ago. I can't remember where it was, where we had that question at the end of here. And we saw that in this circuit, we had of this 3 volts, 0.9 went that way, 2.1 went that way. So, but how? So my question is, if it's not split evenly, how is it decided what the split will be? So it could be 5 and 1, for example. It could be 4 and 2. It's going to add up to 6. But how do we know what it's going to be? Well, the answer is it depends on the resistance of these components. The bigger the resistance, the more of the voltage they will get. So for example, if this is 2 ohms and this is 1 ohm, essentially what that means is that this is going to get more of the voltage than this. And it's in proportion to how much resistance there is. In total, there are 3 ohms of resistance in the circuit, 2 plus 1. This makes up 2/3 of the total resistance, doesn't it? Because it's 2 out of 3, essentially. And therefore, it gets 2/3 of the voltage. It gets 4 volts. This one makes up 1/3 of the resistance in the circuit, which means it pulls 1/3 of the voltage and gets 2 volts. 2 add 4 is 6. So that's how that actually works. I'm telling you this because I know how important it is to understand this because it makes certain questions so much easier. Um, Let me explain again what else I could do. If, for example, this is a light bulb, right? If I wanted to turn this light bulb off somehow, okay, without a switch, one way to do it would be to use a resistor here with a massive resistance, like 1,000 ohms. Because if I use 1,000 ohm resistor, now what's happening here is that this is making up 1,000 ohms out of a total of 1,001 ohms. You see that? There's one there, 1,000 there. In total, there's 1,001 in my example, which means it's getting this fraction of the 6 volts. 1,000 out of 1,001 times 6 is going to be pulling 5.99 volts from that, which means that this is only going to get 0.01 volts, essentially turning it off, right? I mean, it's a tiny voltage, but you can exaggerate this a bit even further. If I made that number even bigger, it's going to get 5.99999. That's going to get a tiny amount, and it's going to be off. So the point I'm trying to make is that by messing around with the resistance of other components, you can redirect voltage to different places in a circuit. So if I now wanted to turn this lamp on, what I could do is use a resistor with 0 ohms. Now what's going to happen? If that's 0, It means it's not got any resistance. This is an unrealistic scenario, but it means that it's not going to get any of that voltage, and all of that 6 volts is going to go here. They're still sharing it. It's still 0 and 6. They're still making up 6. It's just what we're doing is redirecting where it goes. And what this allows me to tell you now, I'm just going to make this up myself, is essentially something about a light dependent resistor. Okay. In fact, let's do a thermistor, and then I can do the exam question. Right. A thermistor is a component whose resistance changes depending on how hot or cold the surroundings are. A thermistor specifically, and this makes it different from a light bulb and stuff, when it's hot, its resistance goes down. When it's cold, its resistance goes up. It is a special component that we use to turn things on or off depending on how hot or cold it is. Okay? So let me tell you how we can use a thermistor. Well, let's do this. Right. I want to do it sideways for some reason. Okay. Here is a circuit. Here is a thermistor. And here is a heater. I'm going to call it H for heater. Okay. So what I would like to happen is for this heater to turn on when it's cold. That's what I want, right? I want it to be nice. And when it's cold, I want the heater to turn on by itself. That's what I want. So think of like you might have a thermostat in your home, which turns on when it gets quite cold in the house and it'll turn on by itself. Or your car, you can set the temperature and when it gets cold enough, it'll turn on to keep it warm. In the same principle, we're going to try and make this work. Okay, just to warn you, this isn't going to work. Imagine this is a 6 volt battery. So what I want is that when it gets cold, I want this heater to turn on. Okay, that's what I want to happen. Now, when it's cold, the resistance of this component is really big. You see, that's a fact. That when it's cold, its resistance is really big. That means, let's again pretend that this heater has a resistance of 2 ohms, it's fixed. Let's pretend that now that's cold, this resistance goes to a really big number. Make it 10,000 if you like, just for the sake of it. Okay, what's going to happen now? Remember, this voltage is shared by these two components based on the resistance. So because this is so big and so much bigger than this, it's going to pull most of that voltage. If you want to know the exact number, it's going to get 10,000 out of 10,002. That's the fraction of the resistance that it makes up, times 6, which, I mean, I've just exaggerated this so much, but it's going to be silly. It's going to get, see, 5.998 of that 6, and this is going to get a tiny amount. The heater's basically not going to work at this point. It's going to be off, which isn't what I wanted. I wanted that if it was cold, so right now it's cold, I wanted the heater to turn on. But because this is pulling all of the voltage, it's not going to turn on. So how do we resolve this? I shall tell you. What we do is, this is still 2 ohms. We don't put the heater there. We put some other resistor here, just a normal resistor. And then we actually put the heater around here like a parallel circuit. Okay, that's what we do. Now what's going to happen when it's cold is the resistance of this thermistor will get really high. Let's pretend 10,000 again, just for the sake of it, right? Which means that it will pull most of that 6 volts. And very little will go to the other component, which is just the resistor, doesn't do anything. So you see, because this is getting 6 volts now, and it's set up as a parallel circuit here, this will also get 6 volts, and it will turn on, which is what I wanted to happen. I wanted it to be on when it was cold. It didn't work as a normal circuit. It was off when it was cold. But this way, it's on when it's cold. And if it gets warmer, let's say it's hot now, right? This resistance of the thermistor will decrease. Let's say it goes down, to exaggerate the point, down to 0. What's going to happen to the voltage share? Well, this is now going to get no voltage and the heater will be off. And this is going to get all of it, and that doesn't do anything. So all we're doing is moving the voltage from one place to another by messing with the resistance of these components. We're just moving it so that we can turn something on and then turn it off and then turn something on and turn it off. That is how this works. Last thing I'm going to do then, which is a question that I had ready. Um, Okay, you will see something here that looks somewhat familiar. It's very similar to the thing I just drew. Okay, we have a circuit used, but basically we're talking about a vending machine here, just so you know. I've skipped a couple of questions at the beginnings, but there's a vending machine here. Um, and we are showing part of a circuit that used to monitor the temperature in the vending machine. The way this vending machine works is that if it gets a bit too hot, it needs to turn on its cooler. It's a bit like a fridge, right? You need to turn on the cooler to keep the chocolate at the right temperature. And it basically the question for 5 marks here, which I'm going to do in basically one line of working out. Okay, so just to prove a point. There is a longer way to do this question. I'm not worried about the longer way for now. I want to get you to understand this because then you understand things like thermistors and stuff. The cooling system inside the vending machine turns on when the temperature of the thermistor is above 20 degrees C. Determine the potential difference across the thermistor. That's here. We have put a voltmeter here. There's a thermistors here, by the way. There's a thermistor. We put a voltmeter around it to measure the voltage here. Determine the voltage across the thermistor when the temperature is 20 degrees C. Now we have a graph here that tells us how the resistance of the thermistor varies with temperature. What I can do is go up from 20 and read across here, and that tells me that the resistance is 80 ohms at when the temperature is 20. Remember, thermistor's resistance changes depending on the temperature. So at 20 degrees, the resistance is 80 ohms. So I know that this thermistor is 80 ohms. Okay? There is another resistor in the circuit that's just fixed at 400 ohms. This is a fixed resistor. It doesn't change. Okay? And the question is, what will be the reading on this voltmeter? I'm just going to do this in one line of working and show you that you've got all 5 marks, all right? Remember what I said about this voltage. It's split between here and here, right? It's shared. Some of it goes there, some of it goes there, depending on the resistance of these components. Okay? And in total, the resistance is 480 right now. So that's 80, that's 400, that's 480 in total. Out of that 480, how much is coming from the thermistor? 80, which means it will keep that fraction of this 12 volts. So if you times that by 12, this will get 2 volts of that 12, and this will get the other 10. That's all 5 marks because there is a longer way to do it. Okay, but I want you to understand it that way so that you can sort of understand how thermistors actually work and how light dependent actually work. They are basically reallocating the voltage from one place to another. And that is why it's 2 volts. But there is a longer explanation for that, which is to do with calculating the current in the circuit, then working out the voltage using that value and using the formula. But understanding that this is how it's split. I think a lot of people just don't appreciate this. Um, and so I think it's just good to do it because it helps answer questions quite quickly. I mean, that is a 5 mark question that I've literally done there, just to be clear. And the answer is 2 volts, and you'd get all 5 marks for it. Right, I think that's it. I'm not doing any more. Everyone seems to be flabbergasted with that, and there's no questions. So I'm going to leave it there. And next week, over the weekend, so people who attend on Friday, you're doing electricity this time, just to be clear. Yeah, everybody. And then from the weekend onwards, you are doing, I think in your year 10, you're doing the sine and cosine rule. No, sorry, year 11 is doing the sine and cosine rule. Year 10 is doing surds and indices, I believe. So enjoy that.